Welcome to my 46th tutoring session in A-level chemistry. In this video, I'll explain as to how the number of carbon atoms and branching influences the boiling points of alkanes, alcohols and carboxylic acids. Don't forget to subscribe my channel, share, like, comment and watch the full video. Now the number of carbon atoms and branching definitely has a profound influence on the boiling points of alkanes, alcohols and carboxylic acids. Now the influence of the number of carbon atoms and branching on the boiling points of the organic compounds is limited not only to these three classes of organic compounds, that is alkanes, alcohols and carboxylic acids. It is equally applicable to other class of organic compounds like aldehydes, ketones, esters, ethers, alkyl halides and other class of organic compounds. I have considered alkanes, alcohols and carboxylic acids as representative examples to explain the influence of the number of carbon atoms and branching on their boiling points. Now there are three major forces that influences the boiling point of an organic compound. It could be a van der Waals force, hydrogen bonding or dipole-dipole interaction. So it could be one of these forces influencing the boiling point, or it could be more than one force. Like in case of alkanes, it is only the van der Waals force, that is predominant force, influencing the boiling point, while in case of alcohols, it is both van der Waals force as well as the hydrogen bonding. So let me begin with the alkanes. And let's see how the number of carbons and the branching influences the boiling points of the normal alkanes or the straight chain alkanes. Now this particular table gives the first 7 names of straight chain alkanes in the homologous series and their structural formula. You can clearly see that as the structural formula of the alkane changes, there is a corresponding change in the melting point as well as the boiling point. So there is not only a change in the melting and boiling points of the alkanes with the change in the structural formula, we also see beyond a particular point there is a corresponding change in the physical state of the organic compound, that is the alkane. So you can see beyond butane there is a transformation from the gas state to the liquid state. So with the change in the structural formula of alkanes, we see that there is a corresponding change in the melting point, boiling point as well as the change in the physical state. So before I get on with the explanation, I would like to add a brief note on 3 types of prefixes that are generally encountered in the alkanes, that is naming the alkanes using the common system. So one should be familiar with these 3 types of prefixes when you're naming the alkanes. That is naming alkanes as per the common system. These 3 prefixes are N, iso and neo. Now the prefix N stands for normal or straight chain alkanes. So this prefix is generally used for alkanes without any branching, that is the alkane that is unbranched. For example, N-pentane. So in case of N-pentane, you see the carbon atoms are arranged in a sequential order in a straight chain without any branching, where N stands for normal or straight chain alkane. So you can name this alkane as N-pentane, and pentane because there are 5 carbon atoms. And prefix iso is used for those alkanes which have one methyl group attached to the second carbon in the chain. So this is the structure for isopentane. As you can see, there is a methyl group attached to the second carbon. And the prefix neo is used for those alkanes which have 2 methyl groups attached to the second carbon, like in case of neopentane. You can see that there are two methyl groups attached to the second carbon. Now here is a graph depicting the impact of the number of carbons on the boiling point of normal alkanes. That is from methane to heptane. So we are considering the first 7 alkanes in the homologous series. That is from methane to heptane. The graph clearly depicts that with the increase in the number of carbons, there is a corresponding increase in the boiling point. As we move from methane to heptane, we observe that there is a corresponding increase in the number of carbons. That is the length of the hydrocarbon chain increases. And as a result, with the increase in the number of carbons or the hydrocarbon chain length, the intermolecular forces also increases. Here the predominant intermolecular force is the van der Waals force that is operative. So with the increase in the hydrocarbon chain length, the intermolecular forces also increase. And as a result, you see a corresponding increase in the boiling point of the alkanes. And in case of pentane, it has a long chain and it's a straight chain alkane. The surface area is more and this allows closer packing of molecules. Now this bracket symbolizes the close packing of the alkane molecules. So as a result of close packing, more energy is required to overcome the forces. And that is why beyond a particular point, you can see there is a transformation from the liquid state to the gaseous state. So up to butane, that is methane, ethane, propane and butane, they are gaseous in nature, while pentane, hexane and heptane are liquid in nature. Because beyond butane, the number of intermolecular forces increases. As a result of the increase in the attractive forces, you can see a transformation from the gaseous state to the liquid state. So what you observe as you move from the methane to heptane in the homologous series of alkanes, the number of carbon atoms increases. As a result, the number of electrons in the electron cloud also increases. And this leads to increase in the induced dipole-dipole forces. And at a particular point, it leads to a stronger intermolecular forces, that is London force is operative, and this leads to increase in the boiling point because more energy is required to overcome the strong intermolecular forces. So the straight chain alkanes, the flexibility is more, surface area is more, and this leads to increase in the number of contact points, and therefore this allows a closer packing of molecules. Now what about the influence of branching on the boiling point of alkanes? Now here are the names of 5 isomeric alkenes with their structural formula and boiling point. Now isobutane is a chain isomer of butane with the branching in the second carbon, and you can see with the branching there is a decrease in boiling point from 0 to minus 12 degree Celsius. And even in case of the chain isomers of pentane, you can see with increase in branching there is a decrease in boiling point. Now pentane has a boiling point of 36 degrees, while isopentane with branching in the second carbon, you can see a corresponding decrease in boiling point. The boiling point decreases from 36 to 28. And with further increase in branching, in case of neopentane, you can see further decrease in the boiling point. So as you move down the isomeric series of pentane, isopentane and neopentane, you can see a corresponding fall in the boiling point, and this is due to branching. So what has branching to do with the fall in the boiling point? The answer lies in the length of the alkane chain as well as the branching. Now in case of pentane, it is a long chained aliphatic hydrocarbon without any branching, and therefore it offers more surface area. So with the increase in the surface area and the contact points, the number of intermolecular forces increases. So the number of carbon atoms increases, number of electrons increase, electron cloud increases, the molecule is more flexible with increase in surface area, and this leads to closer packing of the alkane molecules as more contact points are available. So number of the intermolecular force, that is London forces, increases, and this leads to stronger intermolecular forces, and thereby we see a corresponding increase in the boiling point as well as the melting point of alkanes. The number of carbon atoms and the branching influences not only the melting point but also the boiling point of the particular class of organic compound. Now what about alkane with branching? So let's consider neopentane as an example. So in case of neopentane, as you can see, it offers less surface area and therefore the number of intermolecular forces reduces. Now neopentane is a short chain alkane with branching, and therefore because of the branching and the chain being of shorter length, it becomes more compact with fewer number of contact points. Now with branching, the molecule becomes more compact with fewer number of contact points, and this leads to lesser intermolecular forces, and this affects the boiling point. So when you compare and contrast pentane to neopentane, you can see the surface area offered by pentane is more as compared to neopentane. So the decrease in surface area of neopentane is because of branching. So there is more contact points in case of pentane as compared to neopentane. So the increased number of contact points and surface area in pentane as compared to neopentane, and this accounts for the fall in the boiling point of neopentane. So in case of alkanes with branching, that is, as the branching increases, the molecules become more compact, the surface area decreases, the contact points as a result it decreases, and this leads to reduced induced dipole-dipole forces, and this leads to weaker intermolecular forces, and the number of intermolecular forces as well decreases, and there is less flexibility. So in case of molecules with branching, the flexibility is less, and the end result is there is decrease in the boiling point. So with the increase in branching, the molecule becomes more compact, decrease in the surface area. So with the smaller surface area, the intermolecular force of attraction are diminished, requiring less energy to go from the liquid state to the gaseous state. So less energy is required to overcome the intermolecular forces in case of neopentane, while more energy is required to overcome the intermolecular force in case of pentane. And that is why you see the difference in the boiling point. So when I say less energy or more energy, it is the thermal energy. So more thermal energy has to be provided in order to overcome the intermolecular force between pentane as compared to neopentane, because more intermolecular forces are operative in case of pentane as compared to neopentane. So therefore, more thermal energy has to be provided in case of pentane in order to overcome the intermolecular forces as compared to neopentane. Now here's a graph depicting the influence of branching on the boiling point of isomeric pentanes, that is pentane, isopentane and neopentane. Now, pentane is a straight chain alkane, while isopentane and neopentane are branch chain alkanes. So, all these three come under or fall under the chain isomers, and these are the isomers of pentane. Now, there is a decrease in the surface area with increase in branching. So, the surface area offered by isopentane is less as compared to the surface area offered by pentane. So, the branched alkane with the least or the lowest surface area is neopentane. So, neopentane is a short chain branched alkane. It is a compact molecule with lesser surface area. So, with the increase in branching, the molecule becomes more compact, decreasing in surface area. And with the smaller surface area, the intermolecular force of attraction are diminished, requiring less thermal energy to overcome the intermolecular forces to go from the liquid state to the gaseous state. So, the increased number of contact points and more surface area in case of pentane as compared to isopentane and neopentane. So, neopentane is more compact with fewer contact points and lesser intermolecular forces due to branching. So, with the increase in branching, less thermal energy is required to overcome the intermolecular force between the molecules. So, less thermal energy is required to overcome the intermolecular forces between molecules with branching when changing from a liquid to a gaseous. Now, here's a graph depicting the impact of number of carbons with a terminal OH group. So, moving on to the next class of organic compound, that is alcohols. Now, let's see how the number of carbons in case of alcohols influences the boiling point. Now, in case of alcohols, we find that as the number of carbons increases, you can see a corresponding increase in the boiling point. Now, here you see the first 8 names of straight chain alcohols in the homologous series, that is methanol, ethanol, propanol, butanol, pentanol, hexanol, heptanol, and octanol. With the increase in the number of carbons, you see a corresponding increase in the boiling point. Now, there are two forces operative in case of alcohols. One is the van der Waals force, other is the hydrogen bonding. On one side of the molecule, you see that the van der Waals forces are operative, while the other end of the molecule with a terminal hydroxyl group, you will find the hydroxyl group is further strengthening the intermolecular force by hydrogen bonding. And because of the additive effect or the synergistic effect of these two forces, it leads to a corresponding increase in the boiling point. Now, in case of propanol, this is a very crude way of explaining the intermolecular additive force. You find there are 3 van der Waals forces, as there are 3 carbon atoms and 1 hydrogen bonding. So, totally there are 4 forces operative. And in case of butanol, there are 4 van der Waals forces and 1 hydrogen bonding, leading to a total of 5 forces. While in case of pentanol, it is 5 plus 1, 6 forces involved. So, with the increase in the number of carbons with the terminal OH group in case of alcohols, there is corresponding increase in the boiling point. But the drawback is that with the increase in the number of carbons, the solubility, water solubility falls or it decreases. So water solubility decreases with increase in the number of carbons. So there are two things happening here. One is a corresponding increase in the boiling point. At the same time, there is a decrease in the water solubility. So with the increase in the length of the hydrocarbon chain, the lipophilicity of the alcohol molecule increases. So water solubility decreases with increase in the number of carbons, that is the hydrocarbon chain. So as the hydrocarbon chain increases, the water solubility of the alcohol decreases despite the presence of the hydroxyl group. Now in this particular graph, we see the influence of branching on the boiling point of isomeric alcohols. So we have considered three isomeric alcohols, 1 butanol, 2 butanol and 2 methyl 2 propanol. So 1 butanol is a primary alcohol. Isobutanol is a secondary alcohol, also called a secondary butyl alcohol. And 2 methyl 2 propanol is a tertiary alcohol. It is tertiary butyl alcohol. So we can see that with increase in branching, there is a corresponding decrease in the boiling point. Now alcohols are organic compounds with hydroxyl group. Now the functional group in case of alcohols is hydroxy group, that is OH group, that is covalently bonded or attached to a alkyl group. Now here R, capital R, refers to the alkyl group. Again, there are two forces operative in case of alcohols. One is van der Waals force, other is the hydrogen bonding. So the boiling points of isomeric alcohols decrease with increase in branching. But the boiling points of alcohols are much higher than the corresponding alkanes. Like for example, now 1 butanol has a boiling point of 118 degree Celsius, while butane, its boiling point is 0 degree Celsius. Now the difference in boiling points between butanol and butane is because of the hydroxy group. In case of butanol, you find the presence of one hydroxy group that is engaged in or that can participate in hydrogen bonding. While in case of butane, there are no OH groups or hydroxy group that can participate in hydrogen bonding. So in case of butane, which is an alkane, there is only van der Waals force which is operative or which is a predominant force, while in case of 1 butanol, which has a hydroxy group, we find two forces operative. One is the van der Waals force, other is the hydrogen bonding. Therefore, the boiling points of alcohols are much higher than the corresponding alkanes. And another aspect is that the solubility of alcohols decrease with increase in the hydrocarbon chain. So as the hydrocarbon chain increases, the solubility decreases. Now moving on to the next class of organic compound, that is carboxylic acids. Now this graph explains the effect of branching on the boiling points of isomeric carboxylic acids. That is 1 pentanoic acid, 3 methyl butanoic acid and 2,2-dimethyl propanoic acid. So all three are isomers or isomeric carboxylic acids. And we can see that with increase in branching, there is a corresponding decrease in the boiling point. Now carboxylic acids are a class of organic compounds with the functional group COOH, that is carboxyl group. Now carboxylic acids have the functional moiety, that is carboxyl group, that is covalently bonded or attached to the alkyl group. So here we are talking about aliphatic carboxylic acids. So again, in case of carboxylic acids, there are two forces operative. One is the van der Waals force, other is the hydrogen bonding. So the carboxyl group, as shown in this figure, it can also participate in hydrogen bonding because of the presence of bipolar OH group. And you can see the hydrogen bonding between the hydrogen atom with a partial positive charge. It is covalently bonded to an electronegative oxygen atom with oxygen atom with a lone pair of electrons on another molecule. So again, two forces are operative in case of carboxylic acid. One is the van der Waals force, other is the hydrogen bonding. So boiling points of isomeric carboxylic acids decrease with increase in branching, and the boiling points of carboxylic acids are much higher than those of corresponding alkanes. And same explanation holds good even for carboxylic acids, as I've already explained in case of alcohols. And even the solubility of carboxylic acid decreases with increase in the hydrocarbon chain. So low molecular weight carboxylic acids like acetic acid and propanoic acid are freely soluble in water, while carboxylic acids of higher molecular weights, they are less soluble in water because of increase in the hydrocarbon chain. So the lipophilicity increases with increase in the hydrocarbon chain, and therefore the solubility decreases. Now here we see a graph, an interesting graph, where we can see the impact of the number of hydroxy groups on the boiling points of ethanol, which is a monohydric alcohol with one OH group, ethylene glycol, which is a dihydric alcohol with two OH groups, and glycerol, which is a trihydric alcohol with three OH groups. So monohydric alcohol is that particular alcohol with only one OH group. Dihydric alcohol has two OH groups, while trihydric alcohol has three OH groups. So in case of monohydric alcohol like ethanol, due to the presence of only one OH group, it can participate in hydrogen bonding or engage in hydrogen bonding with one other alcohol molecule. And in case of ethylene glycol, there are two OH groups that can participate in two hydrogen bonding interactions. And in case of glycerol, which has three OH groups, it can participate in three hydrogen bonds. So with the increase in the number of OH groups, the number of hydrogen bonds also increases. So though the operative force is only hydrogen bonding, in case of these three alcohols, there is change in the, or there is difference in the boiling points, because the number of OH groups are increasing. So with the increase in the number of OH groups, there is corresponding increase in the boiling point. So as the number of hydroxy group increases, the number of hydrogen bonds increase. With the increase in the number of hydrogen bonds, dipole-dipole force increases, and this leads to a stronger intermolecular force. And as a result of the stronger intermolecular forces existing between these molecules, there is a corresponding increase in the boiling point, viscosity increases, solubility increases, while the vapor pressure falls. As the number of OH group increases, number of hydrogen bonds increase, and as a result, due to the increase in the number of stronger intermolecular force, that is hydrogen bonding, vapor pressure falls and the boiling point increases. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in my next interesting tutoring session.